Hey guys, welcome into AP Chemistry Unit 3. With this video, we are talking about the intermolecular forces, IMFs, and gas laws. Okay, so everything in this unit you should have already talked about in 10th grade chemistry, but we're just going to make sure we remember it all. Nothing here should really be new aside from vapor pressure, I believe. Okay, so let's look at vocabulary. We have our intermolecular forces that include Lund dispersion forces, dipole-dipole forces, hydrogen bonding, and ion dipole forces. Okay. We'll talk about phase changes, vapor pressure, kinetic energy with the Maxwell-Boltzmann distribution, and then some of our different gas laws. So the combined gas law, ideal gas law, Dalton's law, effusion, diffusion, and Graham's law. Okay, so I separated into two parts. So the first part's going to talk about intermolecular forces. The second part will talk about our gas laws. Okay, so intermolecular forces, remember, intermolecular are between two molecules. Intramolecular are within a single molecule. Okay, so those two words are very similar, just with a different prefix. Make sure you know the difference between the two of those, but they're essentially the same thing, just depending on whether it's between two molecules or within the same molecule. So what that means, if you have H2O, so if you have water, and if we have two of those molecules, okay, an intermolecular force between two molecules is going to be a force between the partial negative on the oxygen and partial positive on this hydrogen. Between those two. And I'm going to draw a dotted line because it's not a bond, it's just a partial attraction. Okay, so it's intermolecular, between two molecules. Intramolecular forces is within the same molecule. So that's that bond there. Okay. So our four types from weakest to strongest are London dispersion, dipole-dipole, hydrogen bonding, and ion dipole. And we're going to talk about each of these. Okay. So Lund dispersion are the weakest partial attraction between, it's between anything, right? Every compound has this, okay? And it forms a temporary dipole in the molecule. So what's happening with the Lund dispersion force is normally we think of atoms like this image on the left here, where the electrons are all spread around the nucleus. But remember, these electrons are moving. So sometimes the electrons might be more skewed to one side. And during that period of time, there are going to be partial charges. But since the electrons are moving, they're going to go back to being distributed. So it forms a temporary dipoles within a molecule. That's why every molecule has this, because every atom can do this. So examples, SF6, CH4, CO2. These are all nonpolar compounds. But even polar compounds have this, okay? Dipole-dipole compounds are between two polar molecules. This is what we were talking about with those partial charges in the last video, and the partial charge with the H2O above, right? So our HCl, our chloride, is going to have the partial negative. Hydrogen has a partial positive. There is a force of attraction between them, even though there's not a bond there. That force of attraction is our dipole-dipole attraction. Okay, so we can have a dipole attraction between those two, that's our intermolecular, or between the HCl that are bonded, that's our intramolecular. Okay, so our examples here are HCl, CH3Br, and SH2. These are all polar compounds, all covalent, okay, but these all have dipole moments, a permanent dipole moment, right? Hydrogen bonding is the strongest covalent attractive force, and it's between hydrogen and fluorine, that should be an E, fluorine, oxygen, or nitrogen, right? An easy way to remember is hydrogen bonding is fun. It's fun, F-O-N, fluorine, oxygen, nitrogen, okay? So if we have hydrogen bonded to an oxygen, we have hydrogen bonding there. Same thing with hydrogen bonded to fluorine or nitrogen. So HF, H2O, and H3 all have hydrogen bonding. And our last intermolecular force is ion dipole. This is, as it sounds, it's ion dipole. It's an ionic compound. So anytime you have an ionic compound, you have an ion dipole bond. And this is the strongest intermolecular force because between two full charges, two formal charges, not just partial charges. Okay? So those are 4 types of intermolecular forces. So in this table, it kind of summarizes, you have what it involves, so what is taking place, what kind of molecules, whether it's polar or nonpolar, and the strength of attraction. So it goes from lowest to highest. Okay? So the effects on the boiling and melting point, this is attached to the strength of attraction. If we have a lower strength of attraction, it's not going to change the boiling point to melting point a lot, right? It's going to have a slight, it's going to be kind of high, but it's not going to be a really high melting point or boiling point. The stronger the force of attraction, the bigger the elevation, right? So ion dipole, so like salt is really hard to boil or melt, right? So the stronger the forces, the stronger or the higher temperatures needed to boil it because it's a stronger bond, a stronger intermolecular force. Okay. So another effect on intermolecular forces is larger atoms have a higher boiling point because if you have more atoms, you have more of those Lund dispersion forces happening within it, more temporary dipoles. Okay. So if we look at this, the green row up here, we have alkanes. These look a little bit weird, these like chains. These are just carbons attached to each other with hydrogens on them. Okay. This is a form of drawing atoms. It simplifies it. You'll use this a lot in organic chemistry if you take that class in college. But that's what that compound looks like. But as you can see, we have more compounds as we go to the right. Or sorry, not more compounds, more carbons as we go to the right. So the bigger the compound, the greater the boiling point. And that goes for all of these. You see, as they get bigger, the boiling point increases. And the reason for that, the Y here, right? The Y is there's more temporary dipoles happening from the London dispersion forces. Okay, so it's more polarizable. All right. So let's look at a couple questions with this. Okay, the first one is, in which of the following compounds of intermolecular forces include dipole-dipole? All right, so let's break this down for each of these. So we have F2, we have CH4, we have CF4, and we have CH2F2. Okay, so again, it's easier to draw these two or to figure out the intermolecular forces after you draw them. So for F2, this is covalent, it's even. So these are going to have the Lund dispersion forces, but since it's even, it does not have dipole-dipole. CH4, same thing, it's even on all sides. It's not uneven, so just Lund dispersion forces, no dipole-dipole. CF4, same thing, just Lund dispersion forces. Okay, and then CH2F2, it is not even, right? We have two separate, with the fluorines and the hydrogens pull differently on those electrons. So this one's going to have the Lund dispersion forces, but it is also going to have the dipole-dipole force. Okay, so these stack. You can have more than one. You're going to start from the lowest, go up. But the answer is D there because that has a dipole-dipole. Okay, I want you to look at the second question. I want you to figure out the answer there. Okay. So I'm going to give you the answer, but I want you to write the explanation. So for this question here, the bromine Br2 is going to have the greater boiling point than Cl2. Okay, but I want you to explain why. Think about what we talked about on this slide here. Okay. And then for the last question, what is the strongest type of attraction between the atoms circled in the areas below? So between oxygen and hydrogen and nitrogen and hydrogen, right? It's covalent compounds, so we have Lund dispersion forces. It is polar, so we have dipole-dipole. It's between oxygen and hydrogen for the top here, and then nitrogen and hydrogen here. And remember, for hydrogen bonding, that's H with, that's not H, H with fluorine, oxygen, nitrogen. So we have that there. We do have hydrogen bonding. Ion dipole, this is not an ionic compound, it's covalent. So we have these three here. So the question asked for the strongest type. So our strongest type here is our hydrogen bond. But we do have all three types of attraction between those two in the circled regions. Okay, so that is it for the intermolecular forces. Now we're going to talk about some phase changes. So this is going to the gaseous phase. Okay, so remember we have three states of matter: solid, liquid, and gas. In formulas, you'll see these symbols here, the S, L, and G. That tells you if it's a solid, liquid, or gas. Okay, a phase change occurs when you go between these states of matter. So going from a solid to a liquid, like ice melting to water, liquid to a gas, right? If you're boiling water to steam, that's a phase change. And when you do a phase change, you are not breaking bonds, right? So with water, you still have H2O, regardless of which phase you are in. What is happening is you're breaking intermolecular forces. You're breaking those forces of attraction between the molecules. And the stronger the intermolecular forces, the more energy you need to change the phase. Okay, so if you're breaking intermolecular forces, not breaking bonding, this is going to be a physical process, not a chemical change. Okay, and then explain why at 15 degrees Celsius or negative 15 degrees Celsius, H2O is a solid, but CH4 is a gas. So if we look at these, H2O and CH4, CH4 is a nonpolar compound that has Lund dispersion forces. H2O has Lund dispersion forces, but it is polar, so it has dipole-dipole, and it also has hydrogen connected to oxygen, so it has hydrogen bonding. Sorry, that's a weird D. Okay, so in H2O, we have stronger intermolecular forces, so it's going to need more energy to break those intermolecular forces. So at lower temperatures, it's still going to be a solid compared to CH4. Okay. And then this question asks, which of the following best explains why more energy is needed for the process occurring at 110 degrees Kelvin, 110 Kelvin, than for the process occurring at 9 degrees Kelvin. So we're looking at 100 degrees Kelvin versus 9 degrees Kelvin. So area S and area Q. Okay. And remember this graph here, this shows the different phases. So you have solid, liquid, and gas. The flat areas, this are phase change. So this is melting or freezing in the first one. The second one is evaporating or condensing. Okay, so remember that's what this graph means. So it's asking us why is more energy needed in S than needed in Q. Okay, so why is more energy needed to evaporate something than it's needed to melt? Okay, so if we think about it, right, if we go back up to this image real quick, right here. From solid to liquid, our balls, our circles here are still close together. It's just able to move around more freely, right? From liquid to gas, our balls are moving on their own throughout the entire area. Okay, so what's happening here is there's really strong intermolecular forces there. And the liquid, we have kind of strong ones, or not kind of strong, but we do have them still there, holding them close together. And then in gases, there really isn't intermolecular forces holding our gas particles together because they're moving on their own. Right, so if we look at our answer choices here, A, intermolecular attractions are completely overcome during vaporization. That might be a plausible answer. B, intermolecular attractions in the solid phase are weaker than in the liquid phase. That's not right because in the solid they're closer together, so those forces are stronger. C, electron clouds of methane molecules are less polarizable at lower temperatures. That's not true because if we're looking at a single molecule, it's going to be equally polarizable at any temperature. because it has the same number of electrons. The electrons aren't changing. And then D, vaporization involves a large increase in temperature. Well, if we look at S here, it's flat. We're not changing the temperature. We're staying at 110 degrees or 110 Kelvin. So that's not true. So our answer is A. Going from a liquid to a solid to a liquid, we're taking away some of the intermolecular forces, but not all. From a liquid to a gas, we're completely overcoming the intermolecular forces. We're getting rid of all of them. Okay. So make sure we remember phase changes are physical changes where we're breaking those intermolecular forces. Okay, so the stronger the intermolecular force, the more energy is needed. Okay, so van der Waals equation is something that has to do with ideal gases, and we'll talk about this here in a minute, but it's related to size, so I wanted to put it here, and intermolecular forces. Okay, so what van der Waals equation does is it makes up the corrections for gas molecules that are not ideal, which is most gas molecules, right? The equation is in that white box there. You do not need to memorize this, okay? This is not going to be on your formula sheet either, so you should not have to do math with this. But what you do need to know is this part here. So if gas particles have strong interparticle attraction, so stronger intermolecular forces, we would need to alter the pressure term, the A term, since the pressure needs to be corrected. Okay? And remember, this is similar to PV equals nRT, where it's expanding the P and the V terms here. Okay, so if we have strong intermolecular attractions, we would need to alter the pressure term. If our gas molecules are large, we would need to alter the B term for volume. Okay, so strength of attraction, you're changing the pressure. The different size, you're changing the volume. Okay, so moving on to vapor pressure. For vapor pressure, the word evaporation is the process of liquid molecules becoming gaseous independent of temperature, right? If you just leave water out, the water is going to evaporate even if the room doesn't reach 100 degrees Celsius. Okay, and also side note, good thing to know for water, water melts at 0 degrees Celsius, boils at 100. You should probably know this. Okay, but evaporation happens at any temperature. We don't have to be 100 degrees Celsius, but water can evaporate regardless. Okay, that's because our molecules do not all have the same kinetic energy. Remember, kinetic energy, we talk about it as an average. So some will have more kinetic energy, and they can leave the water and become a gas, some of those molecules, right? And when those molecules leave, we have some molecules above the water, and that is our vapor pressure. That's determined by intermolecular forces. A weaker intermolecular force, so less attraction, it's easier to escape the liquid, so it has a higher vapor pressure. We have more of a gas. With a stronger intermolecular force, it's holding together more closely. It's harder to become a liquid, so we have a lower vapor pressure. Okay, so our strong intermolecular forces is the image on the left. The lower intermolecular forces is the image on the right. Okay, I know this is talking about evaporation boiling, but you can see it with different amounts of particles on top. Okay, and then whenever we're collecting gas over water, this is an experimental technique. So we can use a eudiometer to collect gas over water, like this image on the right here. We need to subtract the partial pressure of water from the true pressure of the gas. Because if you have water in this image, right, that blue is the water, you're going to have some of these water particles in this area up here with the gas that you are collecting from this tube. Okay, so we need to subtract that partial pressure from the water first before we talk about the pressure of the gas there. Okay, so let's look at this question real quickly. We have 4 different liquid components in flasks at 20 degrees Celsius, so our temperature is the same. Below, the table identifies the compounds. So in the table here, we have our different compounds. Flask C shows the most particles in the vapor pressure. Which of the following is not shown in the model, but helps explain why C must be pentane? So we're saying that pentane is C. So why is that? Okay, so A says the random motion of particles within the liquid. So all of the liquids, regardless of what it is, does have random motion. That's not going to be a right answer here. B says the relative speeds of the vapor particles in each flask. So we said we're at 20 degrees Celsius for all of them. That's our average kinetic energy for a temperature, right? So our relative speed is going to be about the same. Okay. All right, it's going to be a little different. We'll talk about that here in a minute with kinetic energy equation, but it's not going to affect the vapor pressure as strongly there. Okay. For C, the strength of the intermolecular forces between the particles in the liquid. So if we look at these compounds, these are all nonpolar compounds, but you change the size, right? So they all have Lund dispersion forces, but the bigger it is, the stronger the Lund dispersion. So octane has the strongest Lund dispersion forces, and then pentane is going to have the smallest Lund dispersion forces relatively here. Okay, so that might be a reason why C has a higher vapor pressure, because if it has smaller intermolecular forces, it's going to have more particles going into the gas phase. So that might be an answer. And then D, the structural formulas of the molecules of the liquid and vapor in each flask. They all have the same structural formula, just with a few carbons on them, so that's not going to be the correct answer there. That doesn't have to do with vapor pressure. Okay, so our answer is C there. So vapor pressure has to do with our intermolecular forces. Okay, and then talk about Maxwell-Boltzmann distribution and kinetic energy. This is going to be our last thing before we talk about the gas laws. So Maxwell-Boltzmann distribution has to do with temperature. So remember, temperature is a measure of our average kinetic energy. We have this equation here. So as our kinetic energy increases, our velocity is also going to increase. And then since mass and velocity here are on the same side, they're inversely proportional. So if one increases the velocity, the other one's going to decrease, and vice versa. Okay. So remember our kinetic molecular theory. We said that gas particles are so small that their volume is negligible. So we act like they don't have a volume, and they are compressible, right? Like with a balloon, you can press it in, you can make it smaller. The second one is gas particles are in constant random motion. They're always moving. They're moving randomly. The third one is that there are elastic collisions. This means that molecules collide with each other and the walls without a loss of energy. So that energy is transferred, energy isn't being lost there. Okay. And in 4, there are no forces of attraction or repulsion between the molecules. So this means that if we have two molecules moving past each other, there's not going to be anything pulling them in. So they're not going to like curve. They're just going to move straight past each other. And then 5, the average kinetic energy is dependent upon the temperature, because remember, temperature is our average kinetic energy. Okay, so in which 1 liter flask do the molecules have the greatest average speed? Right, so if we're looking at average speed, we need to look at two things. First, let's look at temperature, because remember, we have Ke equals 1/2 mv squared. So first, let's look at temperature. We want a higher temperature. We have 30, 50, 40, 50, 40. So we know we want one of our 50s. Okay. The second thing is we want some of our speed is our velocity. Velocity is inversely proportional to the mass. So that means if you have a higher mass, we have a lower velocity. If you have a lower mass, you have a higher velocity. So we want the particle with the lowest mass. So is that going to be N2 or O2? It's going to be N2. Okay, because O2 has a mass of 32, N2 has a mass of 28. Okay, so for average speed, we're looking at the temperatures and we're looking at the mass of the compounds. Because the smaller the mass, the higher the speed, the velocity. All right, then looking at the actual Maxwell-Boltzmann distributions, this is a distribution that looks at the number of gas particles and the speed. Okay, so on our graph, the y-axis, we have the number of molecules, that's the particles. And then on the x-axis, we have our speed. Okay, so what we're looking at here is the area under the curve, that area there, that tells us how many particles we have. Okay, so regardless of what it is, all these areas are going to be the same. They're just distributed differently. Okay, where that peak is, that's going to be our average. Okay, so our average for a colder gas is going to have a lower speed. Our average for a hotter gas is going to have a higher average speed. Okay, and it is more distributed. So you can see here, there are some of our cold gas that are moving the same average as our hot gas, but it's a very small amount. Okay, because it is a distribution. Temperature is just an average. So factors that affect the speed is going to be our size of the molecule. So smaller molecules move faster. And then the temperature of the gas. Okay. So let's look at these two real quick. If we have this question here, if the given Maxwell-Boltzmann distribution graph below represents 4 noble gases at a constant temperature, label each curve with a noble gas and explain your reasoning. Okay. So our noble gas, remember, that's the very last group. That's our helium, neon, argon, krypton, xenon, radon. Okay, so we're going to take 4 of those. Let's just take these first 4, and we're going to label them on the curve. So remember, the bigger the molecule, the slower it's going to go. So the bigger one's going to be the slower speed, and then as it gets smaller, it's going to go a little bit faster. So we're going to label it as such. So based on the mass of the molecule, it's going to have faster speed for smaller molecules, slower speed for bigger molecules. Okay. The second question here is on the graph above, show the speed distribution of molecules in a sample of gas at a certain temperature. And it's asking you to sketch a new graph if the temperature decreased. Okay. I want you guys to go ahead and do this one on your own. But if you need help reading these graphs, let me know. All right, so that's end of the first part. The second part, this should say part right here. I don't know where that went. The second part is looking at our gas laws. Okay, so I'm going to go through this a little bit quickly because a lot of these gas laws we've already talked about before. It's just doing math with them. Right, you talk about all these gas laws and either advanced or on-ramps chemistry. But remember, with our units, for temperature, we either report them in Kelvin or Celsius. To convert between them, Kelvin is equal to Celsius plus 273.15. Our pressure, we will typically use atmospheres, but you might see millimeters of mercury, or you might see torr, or even kilopascals, but I doubt you'll see that one. Okay. And those are the conversions between them. So 1 atmosphere is 760 millimeters of mercury, which is 760 torrs. For volume, we always report in liters. You can also see milliliters, right? That's just 1,000 milliliters is 1 liter. Moles is in moles. That's a pretty straightforward one. And then you'll also have the ideal gas constant. These numbers are given to you. However, you need to pay attention to the units, right? They have different gas units, or pressure units. So depending on what pressure you're given, you'll have to use a different ideal gas constant. And then also remember at STP, which is at 273.15 Kelvin and 1 atmosphere pressure, we have the conversion of 1 mole is 22.4 liters for any stoichiometry we need to do. So on your paper, you guys have these relationships. I'm not going to go too much into these because you've already talked about these. They're pretty straightforward. For Boyle's law, pressure and volume are inversely proportional. That means as one goes up, the other one's going to go down. The other gas laws here are all directly proportional, so they both increase at the same rate. Okay, so as pressure increases for Gay-Lussac's, temperature is also going to increase, and so on and so forth. So using those relationships, I want you guys to go ahead and answer these questions. I'm going to give you an answer with the correct number of sig figs. Okay, so I want you to show the work, but I'm going to give you the answers here. 1.1 ATM, 5.4 liters, and then 416 torr. Okay, so I want you guys, so the third one is not two correct sig figs, but the first two are. I want you guys to work through those and try to figure out the sig figs, how I got those numbers. Okay, our combined and ideal gas laws are further uses of those gas laws we just looked at. Okay, the ideal gas law, the combined gas law first, looks at pressure, volume, and temperature, the relationship between those three. The ideal gas law is pressure, volume, moles, and temperature. And here's where we have that ideal gas constant. Okay. And remember, when we say the word ideal gases are at higher temperatures and lower pressures, and it's as small of a molecule as you can be. Okay, so bigger molecules are going to be less ideal. All right, and then just some conversions from these, you can also look at things like density, right? The D term is density, the M term is molar mass, just by using conversions of what density is, what moles are, things like that. Okay. These two questions, again, I will let you do because they are just using math. It is not a new concept. For the first one here, you should get 1.08 grams of H2O. The second one is 7.7 liters. So try to work through those. If you need help, let me know. Okay. And then you guys have these questions, I believe, on the very back of your notes. These are not going to be required. Okay, so this is just extra practice if you want to do them, if you need the extra practice. I'm not going to look at this page for completion. It is just if you need to do this, you can do it. If you feel comfortable with these questions, you know how to do all of them, you know how to calculate density, do the ideal gas law, you should be fine here. Okay, so Dalton's law is pretty simple. You're looking at partial pressures. Okay, so what this means is in a container, we can have this container here, the total pressure, that has two different gases. We have gas A, the red ones, and gas B, the blue ones. The way we know the total gas here, if we don't have our pressure, to find the total pressure, is we're going to add up the pressure from gas A and the pressure from gas B. So 3 plus 4 is our 3 plus 1 is our 4 atmospheres of pressure for the total. So that's what Dalton's law is saying. It's that the total pressure is equal to each individual pressure that you have. So if you have, say, air, you have O2, you have some nitrogen gas, you have some hydrogen gas, right? You have a bunch of different gases in the air. You're going to add them together to get our total pressure. Okay, and the partial pressure, so that term there, that is the mole fraction of the gas times the total pressure. So if you need to work backwards, you're going to have the mole fraction, so the moles of your compound divided by the total moles in your container times the total pressure. That gives you your partial pressure. Okay, so let's look at a couple questions with this. So if we have a container filled with oxygen, hydrogen, and nitrogen, have a total pressure of 740 millimeters of mercury. Oxygen has a pressure of 300. Hydrogen has a pressure of 150. What is the pressure of nitrogen, right? So our total is equal to each individual one added together, right? So that's just simple subtraction. So our nitrogen is 290. Okay, and the way you can report this is because we're looking at partial pressure. You would have partial pressure. Let me write this another color actually. The partial pressure of N2 is 290 millimeters of mercury. Okay, the millimeter of mercury will be in the same line. I just didn't have room there. Okay, And then we have a gas mixture at 0 degrees Celsius in 1 atmosphere contains 0.010 moles of H2, 0.015 moles of O2, 0.025 moles of N2. Assuming the ideal behavior, what is the partial pressure of hydrogen gas? Okay, so we need to know the total first. So 0.01, 0.015, and 0.025 gives us 0.05. Okay, that's our total. We don't have moles though, right, but we have our total pressure. The partial pressure of H2, oh sorry, we do have moles. That was the number that gave us. So that's the number of moles. We have 0.05 moles total. So a mole fraction is the 0.01 divided by 0.05. That is about 20%, right? You would get 0.2 from that. Okay, so we know it's about 20% of the mixture, and we have our pressure. It's 1 atmosphere. So 1 atmosphere times 20% is 0.2 atmospheres. So our answer there is C. All right. Okay, and then our last concept here with Graham's law, we have 2 terms for the movement of gases, effusion and diffusion. Diffusion is what you're used to. This is just gases spreading out, right? If I pop a balloon in a room, the gases in the balloon are just going to spread out throughout the entire room. Effusion is you're escaping through a hole, right? So if I poke a small hole in the balloon and the gases are escaping through that, that is effusion. But if I just pop the entire balloon, that's diffusion because it's spreading out evenly. Okay, so what Graham's law says is that the rate of diffusion is inversely proportional to the molar mass of the gas. Okay, this equation here, I don't believe, let me check actually. I'm not certain if it's on your reference sheet, so let me make sure about that. Okay, this is not on your reference sheet. So you may not have to do the math with this, but you should know the concept here. Okay, at least on the AP test, you will have to do the math on the practice packet. Okay, so what this is saying is that the rate of diffusion is inversely proportional to the mass, to the molar mass. Okay. So these are actually switched on here. I will make sure to switch it on the notes before we look at that, but this 2 and this 1 should be switched. Okay, so inversely proportional means that they are opposite sides. Yes, okay. So what this looks like is if we have the rate of effusion for argon was measured at 0.218 moles per second, calculate the rate of effusion for helium gas. Okay, so we have our equation. We have R2 divided by R1, the rate, is the square root of the molar mass of 1 divided by the molar mass of 2. Okay, so we have our 2 compounds. We have argon, we have helium, and we have 1 rate. So I'm going to put that one on top just to make it easier. So our argon is going to be on top, divided by our rate of, we want helium, is equal to the square root, the molar mass of helium, right? Helium has a mass of 2, but we have, if it's a compound, we have 2 of them, right? Or sorry, helium has a mass of 4, not 2. It has 2 protons, 2 neutrons. So 4.0026 from the periodic table. And then argon has a mass of 39.948. Okay. And then this is just mass. You would do this division, take the square root, and then you would need to switch these 2. So multiply by R of H2, or R of He on both sides, then divide by what you get from this term here. So 0.218 divided by that term should give you R of He is 0.689. And our units are moles per second. right? That was given in our question here for the rate. Okay, so I want you to try to do this question here. This is a little bit more difficult, but 4 times faster. So the rate of an unknown gas is 4 times faster than the rate of oxygen gas. So you have one mass. For the rate, if it's 4 times faster, just pick a number. So the rate of oxygen is 1. So 4 times that is going to be 4. Okay, so you have your rates, you have your molar mass of oxygen. You're trying to find the molar mass and the identity of your unknown. Okay, I want you guys to work through that. If you need help, let me know. But you should get your answer. That's hydrogen gas, H2. Okay, so that is the end of Unit 3, intermolecular forces and gas laws. Remember, if we have questions, make sure to ask. But hopefully this unit was a little bit easier because we talked about all this in 10th grade chemistry already. All right, have a good day, and I'll see you during the next unit.